can we get some of the metabolic benefits of endurance exercise, such as muscle regeneration, fat burning, and cellular health, without stepping foot on a treadmill? This possibility is becoming a focus of modern longevity research through a technology known as Pulsed Electromagnetic Field Therapy, or PEMF. While the United States Food and Drug Administration approved PEMP therapy back in 1979 for healing bone fractures, modern research is uncovering its effects on muscle and systemic metabolism. To understand how this technology interacts with human biology, it's necessary to examine the underlying cellular mechanisms which act as a foundation for understanding how our tissues respond to magnetic fields. A core component of this biological response is a specific calcium channel on the cell membrane called transient receptor potential canonical 1, or TRPC1. Research indicates that TRPC1 channel acts as an antenna for magnetic fields. When stimulated by low-energy pulsed electromagnetic fields, the TRPC1 channel allows calcium ions to enter the cell. This influx of calcium activates a signaling cascade that directs the cell to grow and adapt, emulating the signals naturally produced during physical exercise. This mechanism triggers a biological process termed magnetic mitohormesis. Hormesis is the principle where a mild, temporary stress induces an adaptive survival response that strengthens the biological system. Pulsed electromagnetic fields create a mild stress on the mitochondria. This mild stress triggers an adaptive response to generate more mitochondria and prompts the body to turn energy-storing white fat into metabolically active brown fat, which burns calories to generate heat. Data from the laboratory models demonstrates that these benefits are highly specific to time and amplitude, defining a strict magnetic efficacy window. A single 10-minute exposure to low-energy magnetic fields of 1 or 1.5 millitesla is sufficient to activate these regenerative and respiratory pathways. Conversely, prolonged or repetitive magnetic exposure can cause excessive oxidative stress. To see how these cellular mechanisms translate to systemic human biology, researchers have traced how pulsed electromagnetic fields mimic endurance exercise by activating the master regulator of mitochondrial gene expression, PGC1 alpha. This is the identical molecular pathway activated by physical training. The activation of this pathway promotes the development of endurance-based slow-twitch muscle fibers. Unlike sprint-focused fibers that burn through glucose quickly for rapid bursts of speed, endurance fibers are packed with mitochondria and specialize in burning fat for sustained long-term energy. Skeletal muscle operates as an endocrine organ that releases beneficial signaling molecules called myokines into the bloodstream. When muscle tissue is activated by the specific pulsed electromagnetic field protocol, it stimulates the muscle's internal communication system to release beneficial proteins, such as the hormone irisin. Irisin is an exercise-induced hormone that travels through the bloodstream to drive fat burning, support brain health, and strengthens bones, serving as a primary messenger for the systemic anti-aging benefits of physical activity. This metabolic activation also addresses the accumulation of toxic lipid species. Physical inactivity causes toxic lipids called ceramides to accumulate in muscle tissue and blood, which contributes to insulin resistance and mitochondrial dysfunction. The data indicate that pulsed electromagnetic field therapy helps muscles burn these fatty acids, which lowers toxic ceramide levels and stabilizes systemic metabolism. To evaluate whether these biological mechanisms produce tangible health outcomes in living populations, researchers moved from laboratory models to human clinical trials. One community case study focused on older adults with pre-existing mobility issues. 101 participants received a 10-minute treatment to their quadriceps once a week for 12 weeks. After the 12-week intervention, participants demonstrated functional improvements across all major mobility metrics. Instead of just moving faster, their average times on foundational tasks, like standing up from a chair in the timed up and go test, dropped by roughly 2 full seconds from 11.25 to 9.31. In clinical geriatrics, a 2-second reduction on these standard movement tests represents a major shift from a state of high frailty towards functional independence. Performance on the 5 times sit-to-stand test also improved from an average of 12.71 seconds to 10.40 seconds. Normal gait speed across a 4-meter distance increased from an average of 0.98 meters per second to 1.12 meters per second. The impact was most pronounced in the oldest age bracket, spanning ages 76 to 91. Their average walking speed rose from a baseline of 0.79 meters per second up to 0.92 meters per second. This specific increase carries heavy clinical weight. Crossing the 0.8 meters per second threshold effectively moves these individuals out of the high-risk zone for adverse health outcomes, shifting them into the category of community-dwelling independent older adults. When researchers analyzed the participants' body composition after 8 weeks of the once-weekly protocol, they found a 1.2% average increase in skeletal muscle mass. The gain in lean mass occurred alongside a 4% average decrease in total body fat. Crucially, the 4% reduction occurred specifically in visceral fat, the inflammatory fat deposits that accumulate around internal organs. For an older population, reducing visceral fat while simultaneously gaining lean muscle tissue represents a direct reversal of age-related sarcopenic obesity. A separate clinical trial evaluated the efficacy of this protocol on patients suffering from end-stage knee osteoarthritis who were awaiting total knee replacement surgery. This was an 8-week randomized controlled trial involving 60 participants. The participants combined standard home-based exercises either with an active PEMF device delivering a brief 10-minute treatment twice a week or a deactivated sham device. The group receiving the active pulsed electromagnetic field therapy demonstrated significant gains in both knee extension and knee flexion muscle strength compared to the exercise-only sham group. The largest strength gains were recorded in female patients and individuals over the age of 70, while male participants reported the highest level of pain relief. This specific protocol was also applied to patients recovering from anterior cruciate ligament reconstructive surgery. Post-surgical patients using the pulsed electromagnetic field protocol showed improvements in muscle mitochondrial bioenergetics and lower circulating levels of systemic ceramides, which are toxic lipids that contribute to insulin resistance. As promising as these findings look, we have to look closely at the limitations of this study design. The primary community case study looked backwards at data from walk-in volunteers, rather than tracking a strictly selected randomized group from the start, meaning the participants started with highly varied health backgrounds. Additionally, the trial did not restrict the use of outside physical rehabilitation or pain medication, meaning these concurrent factors could introduce margins of error in self-reported pain scores, though data analysis showed outside rehabilitation had no statistical significant impact on the final mobility scores. In transparency, it's worth noting that this research was funded in part by Enterprise Singapore, and the lead investigator holds a commercial patent on the system and method for applying pulsed electromagnetic fields. The lead author is also a co-founder of Quantum TX, the company commercializing the technology, and several co-authors are current employees. While these commercial ties do not invalidate the published data, they provide necessary context for evaluating the research as the technology moves into wider clinical testing. These findings carry significance for longevity protocols because standard physical exercise requires mechanical stress that causes microdamage to muscle tissues. For individuals suffering from severe sarcopenia, age-related frailty, or acute injury, standard exercise is often impossible to perform. PEMP therapy operates by delivering a targeted mitohormetic signal that bypasses mechanical tissue stress while preserving key mitochondrial and metabolic benefits of muscle activation. This discovery opens up a lot of questions about how remote magnetic fields communicate with our cells and mitochondria. What are your thoughts on these findings, and how realistic do you find it to introduce a protocol like brief magnetic stimulation to counteract age-related muscle loss? Drop your perspective in the comments below. Thank you for your attention, and I wish you all well.